about the diatomic molecule. When the temperature is too low, that's when the temperature is too low, we're deep in the quantum regime. And when you're in the quantum regime, the oscillator has exponentially small energy compared to what it would be classically. On the other hand, when the temperature goes up, at some point, the temperature will get larger than h bar omega. At that point, you begin to activate the oscillator. You can't activate the quantum oscillator unless the temperature is such that it corresponds to more than one quantum worth of energy. That's what this says. So where are we? At very low at low temperatures, up to some temperature, the diatomic molecule behaves like a monatomic molecule. You do not stop the vibrations going. But at some temperature, if you raise the temperature enough so that the temperature becomes bigger than the quantum of energy, the diatomic molecule starts to behave like a diatomic molecule. Now, that temperature is pretty high. For a good stiff molecule, here's another point. The stiffness determines omega. The stiffness of the oscillator, what is it, the square root of k over m? The stiffer the oscillator, the larger the frequency. So the crossover point, the stiffer the oscillator, the higher the temperature of the crossover point. Well, molecules are pretty stiff on the scale of rubber bands. And the temperature at which the monatomic molecule, where the molecule goes from looking like a monatomic molecule to being a diatomic molecule, is fairly high. But what happens if you raise the temperature even a little more? Oh, incidentally, often before this happens, something else starts to happen. That molecule starts to rotate, other things start to happen. This is just one example. What happens if you heat it even more? You activate even worse things. The atoms themselves start to vibrate, and eventually they'll get ionized. So when they become ionized, it doesn't behave like an atom at all. It behaves like an electron and a proton. So this is an example of quantum mechanics solving a deep problem that physicists have been very, very confused about. In particular, I'll tell you where this came up. Solids are simply systems of molecules where the molecules are arranged in a lattice. They vibrate around the lattice centers. So each atom is sort of an oscillator. The energy of the oscillators as a function of the temperature, the amount of energy as a function of the temperature determines the specific heat of the crystal. The specific heat of a crystal with a very, very large number of oscillators, or the heat capacity, was estimated by classical physics to be much, much larger than the actual answer. It was Einstein who basically figured out that what was going on is that the quantum statistical mechanics of oscillators suppressed the oscillators until the temperature got high enough. So this is another Einstein, one of his small minor contributions. I thought he got the Nobel Prize for the photoelectric effect. I think so. Okay, but then this is neither of them.
So when was this done? When did he do this? I mean, quantum mechanics had already come in?
No. Right, but remember that Einstein invented quantum mechanics in 1905, so I'm not sure exactly. Somebody look it up, specific heat of solids. No. It was early. It was long before people understood the foundations of quantum mechanics. He just knew that the quantum energy levels had to be proportional to frequency and to n.
So he wasn't opposed to all aspects of quantum
No. No. Yeah.
When we first derived the Boltzmann distribution, it was based on discrete states and the partition function by summing that across all possible states. And then when we looked at the gas, we went from the sum to the integral. And in that transition, we're inherently assuming that the possible states for the position of momentum are uniformly available. Now, is this a reasonable assumption? From the results, it looks like it wouldn't, but I don't know if there's something else to consider behind it. I would think that for the momentum,
Yeah.
we'd expect some equivalence of H bar, so maybe that would be uniform based on that, and the position might be conjugate to that momentum.
I would say the ultimate justification was the quantum mechanics, the quantum derivation of the, for example, ideal gas. But here's an example of where the quantum derivation reproduces in the high temperatures the classical answer. So really the right logic, the real serious logic, is to start with quantum mechanics and show that the quantum mechanical counting of states corresponds to the integral over phase space. And that's true. I just give you an example here. Do the calculation as classical physicists would ordinarily do it. Here it is. And we got, what do we get? Let's go back actually to the partition function itself. Yeah, let's just look at the partition function itself. Not even take the energy. Let's just see how close we get. Okay, this partition function at high temperatures means small beta is 1 divided by 1 minus beta h bar omega, right? H bar is a constant. Incidentally, so is omega, but h bar is a numerical constant that sits in front of all partition functions. Let's not worry about it. 1 over beta omega. Now, what was the partition function that we said for the classical case? Here it is. 1 over beta omega. The 2 pi is, again, a constant, not particularly interesting, but its dependence on beta and omega is 1 over beta omega here, 1 over beta omega here. The quantum mechanics only comes in this multiplicative constant 1 over h bar, which doesn't matter when you differentiate it. So here's an example of the derivation of the classical statistical mechanics from the quantum mechanics, and that's really the right way to go. But let me tell you, this formula was known long before quantum mechanics, so they were doing something right. They intuited that phase space was the right space, xp space, momentum position space was the right way to think about classical systems. Okay,